1991, Kuwait. Tanks speed across the barren desert. But how will this massive strike force get food, water, and shelter? 1968, Vietnam. A wounded soldier is whisked to a nearby field hospital. Who cleared the jungle to build it? 1945, Normandy. How did 1 million soldiers get ashore? Now, the heroic untold story of battlefield engineering on Modern Marvels. Because preparing for battle didn't usually have the drama of the battle itself. Most historians, novelists, and movie makers focused on the fighting rather than the actions preceding the fighting. But history shows in the world of battlefield engineering, there was more than enough drama and fighting to go around. It has been the job of the battlefield engineer to lay the groundwork, quite literally, for the battle to come. They built roads, railroads, and bridges. They constructed airfields, barracks, hospitals, supply depots, and all the other facilities that supported combat operations. They were earth movers and river crossers. They built things and they destroyed things. Their mission was critical because without bases from which to operate, there was no way to mount an attack. Without open supply lines, an army would quickly run out of food, water, and ammunition. The Navy's engineers, the Seabees, have a slogan: we build, we fight.
When I'm asked what do the Seabees do, the short answer is we do anything and everything, and we do it quickly.
Ask an Army engineer and the answer will sound much the same.
Remember one thing, the engineers are the ones who get them in and the ones who get them out. And if you don't believe me, just ask an infantryman, they'll tell you.
Throughout history, man has built fortifications. Building those fortifications and breaking through them give rise to the first battlefield engineers.
There's a dichotomy between warriors and soldiers. Warriors are interested in defeating individuals. They're not interested in conquering a province, defeating an entire army. They don't care what's going on next to them. They care about the one person they're fighting. A soldier is part of a unit, which is part of a greater unit, which is part of an army. He fights as a member of a collective. He has greater goals. And this is perhaps the most profound difference. Military engineering flows out of soldiers as opposed to warriors. Warriors are not military engineers. Soldiers are.
It is strangely ironic that the same engineers who are called upon to devise a defense are often later called upon to devise a way to break through it. The fort begets the battering ram. The more heavily fortified castle begets the siege engine and the catapult. As defenses strengthen, they require bigger, stronger, more lethal ways to penetrate them. Over 2,000 years ago, the Romans decided that if they were going to rule the world, they needed a way to get there. Some of their roads and bridges were so well constructed, they remain to this day. Following the fall of the Roman Empire in the Dark Ages and the Middle Ages, defenders built better and bigger walls, causing attackers to go over or under them.
To counter the wall, to counter the defenses that the engineers had come up with, then machines were created. One of them being the catapult, a way to get over the wall. You threw a rock, in some cases you threw a dead horse, or you threw a dead body to spread disease.
Another way of dealing with walls was to breach them. This was usually done by soldiers called sappers and miners.
Sappers would dig the trenches above the battlefield, and they would trench up to the enemy fortifications, and at the last minute, a group of volunteers known as the Forlorn Hope would attack the fortification walls and destroy them to breach to the soft underbelly inside. Now the miners would tunnel underneath the fortifications to collapse the enemy's walls and breach from the underneath side.
castles were having mines dug under their walls with such frequency that there arose a need for mine detectors.
Mine detection can go back as far as the Middle Ages, when women would carry big copper bowls filled with water down to the basement of the castle or the fortification, set it on the stone floor, and be domestic down there, sewing, cooking, but keeping an eye on the water. And when they'd see ripples developing in the surface of the water, they'd say, "I detect a mine. I detect the vibrations of the picks and the shovels of the miners that are undermining our foundation to collapse our walls."
As fortifications became virtually impenetrable, sieges became less effective. But then in the 14th and 15th centuries, the introduction of gunpowder and cannons changed battlefields forever.
If you have a castle and you could keep your opponent in the field for months, your opponent would end up starving outside your walls. Winter would come, the opponent would not be able to provision his armies, and you won. When gunpowder came along, the opponent knocks down your wall, he marches by you, and he wins. Essentially, gunpowder made the castle obsolete.
Following the death of the castle, the innovative French military engineer Sébastien Volbard proposed a radically new type of fortification. Thick walls low to the ground helped protect from cannon fire. A star-shaped design allowed defenders inside the fort to fire at attackers from virtually any angle. By the time of the American Revolutionary War, the monumental changes in battlefield tactics caused by the use of gunpowder and cannons had completely changed how wars were fought. An army had to have trained and educated battlefield engineers.
In the American Revolution, the Army was created all dressed up to go somewhere off to fight, and found out, gee, guys, we're missing something. We have no engineers. Congress says, let us have some. Let us promote some people to be engineers. No, you don't understand. We have no engineers. We have to hire them.
In 1775, George Washington created what was to become the Army Corps of Engineers. And it was fortuitous that the French, perhaps the best engineers in the world at the time, were more than happy to supply engineers to help defeat the English. After the War of 1802, Thomas Jefferson created the nation's first engineering school at a fort located at West Point, New York. It would be the nation's primary source of engineers and military officers for decades to come. In 1861, the American Civil War introduced the biggest revolution in battlefield engineering since gunpowder: railroads. The ability to quickly transport large numbers of troops to wherever they were needed changed military tactics dramatically. The Northern armies controlled 30,000 miles of America's railroads, more track than could be found in the rest of the world. And they continued laying even more rail even as they ripped up hundreds of miles of Confederate track.
The Union Army in the North had the industrial ability to manufacture locomotives and extend rail lines at a prodigious rate, while the Confederate Army in the South lacked that ability. Railroads were being destroyed and locomotives burned much faster than they could be replaced in the South, creating a tremendous disadvantage for Southern mobility.
Railroad bridges were built and rebuilt again and again during this war. This one was rebuilt 7 times. When Abraham Lincoln saw this bridge over the Potomac, he said it looked like it had been made from bean poles and corn stalks. This bridge over the Chattahoochee River was 800 feet long, nearly 100 feet high. It took over 4.5 days to build. An astounding accomplishment in that or any time period. And timber bridges weren't the only record-breaking projects.
The most significant military engineering development in the Civil War was the advent of the ponton or pontoon bridge. Bridges built across boats or ships date as early as the 5th century BC. But for us, it was a new challenge. Engineers responded to that challenge to the point that in 1864, they built a 2,200-foot float bridge across the James River in slightly more than 10 hours. That's the longest American float bridge built by the engineers in American history.
The success and rapid capture of old-style forts signaled the beginning of the end of fixed masonry forts. They were replaced by massive earthwork fortifications. In the future, trenches would replace walls as the dominant type of defense. The widespread use of mortars and cannons on railroad cars heralded a new, more mobile use of heavy artillery. On a smaller scale, but still ominous note, another innovation appeared that would drastically alter ground warfare.
In 1862, we have a Confederate engineer officer who will put a fuse on an artillery shell and bury that shell in a road. When the Union cavalry comes along, the shell detonates. That's the first use in the American Army of what we would refer to today as a landmine.
The battlefield innovations witnessed during the Civil War provided a glimpse into the future. A half-century later, a war they would call the Great War would continue a trend toward a more entrenched, more horrific kind of combat.
Without battlefield engineers in the American colonies, the British troops had no camps or living quarters. Instead, they were installed in colonists' private homes. This was one of the grievances leading to the American Revolution. Battlefield engineering will continue on Modern Marvels. You are watching Battlefield Engineering on Modern Marvels.
World War I was called the war to end all wars. But it might better have been called the war to begin all modern wars. When the fighting began in Europe in the summer of 1914, advances in the technology of killing took more soldiers' lives in less time than ever before. The world had never seen anything like the trenches of World War I, a far cry from the ditches of previous conflicts. They intertwined for hundreds of miles. Frontline trenches, communications trenches, support trenches, all were tied together in city-like networks by battlefield engineers. At the beginning of the war, generals schooled in classic battlefield techniques were still accustomed to sending vast waves of troops at each other. Because of advances in weaponry and battlefield engineering, these tactics of the past led to human slaughter of almost unimaginable proportions, especially when troops were ordered to attack. During the Battle of Verdun, one of the bloodiest battles in the history of the world, it is estimated that 400,000 French soldiers and 600,000 Germans lost their lives in just 6 months.
Trench warfare had to be the worst situation when one had to eventually go over the top. And in that case, no man's land must have seemed like an eternity to reach the other side. Many people didn't reach the other side. You had landmines, you had barbed wire. Barbed wire was there not only to slow you down, but to literally ensnare you, to allow the Grim Reaper of the First World War to do its grisly work, the machine gun, to take out entire units.
With miles of barbed wire to get across, battlefield engineers needed the newly introduced tank to break through the barriers and roll over obstacles. The tank led to the development of the anti-tank mine, which in turn led to a need to breach minefields. Although the full impact of military aircraft would not be felt until World War II, their introduction here created a whole new set of problems and challenges. Targets far behind the front lines, which were previously safe, were now vulnerable to attack. And an army's position and movements were open to surveillance from the air. Since the days of the Greeks and Romans, wars were won by the army that could move the fastest. Motorized warfare took fighting to a new level of speed and conferred on battlefield engineers a heightened level of importance.
World War I was also important to the engineers in that it is the point in which the engineers begin their love affair with the internal combustion engine. It marks the beginning of the engineers' shift from horsepower and manpower to machine power. That evolution has continued to today. Without the machinery of today, the engineer's job would be virtually impossible.
Roads that were built to handle horse-drawn carts had to be improved to handle the faster, heavier gasoline-powered vehicles. Bridges had to be stronger. Rail lines had to be repaired. To a large degree, without engineers in the battlefield, no one could move. When the United States entered the war in 1917, the first request from the British and the French governments was for engineers. Newly organized railway regiments and combat engineers rushed to France. Not surprisingly, the first U.S. casualties were engineers. This was the war that formalized the concept of fighting engineers. Prior to this, engineering divisions were separate from combat units. Now they were expected to carry shovels and rifles, hammers and hand grenades. When American engineers began to arrive in big numbers, their effect was immediate.
The Germans would blow up the bridges, but the Americans would rebuild them. They'd blow up the switches, and the Americans would rebuild them. They couldn't successfully blow up every foot of track, so we'd use what was left.
Behind the lines, the engineers' efforts of building ports, roads, railroads, and support facilities produced some staggering statistics. The 20th Engineers, the U.S. Army's largest regiment, helped produce 200 million board feet of lumber and 4 million railroad ties.
The scope of the American war effort, which only lasted a couple of years, was truly amazing. We brought 2 million men to France, and we had to feed them. And the engineers were responsible for making sure that we had fresh American food for these soldiers.
To satisfy a tremendous need for food refrigeration, one ice-making plant produced 500 tons of ice per day. Another refrigeration plant could store over 5,000 tons of beef. American engineers constructed a bakery that baked 4,000 tons of bread a day. But the most telling statistic of the war involved people, not war supplies. Experts say 14 million soldiers and civilians may have died. It would now be up to battlefield engineers to figure out ways to defend against an even more terrifying war machine that would soon roll through Europe. Following World War I, the leaders of France decided to protect the country by constructing an elaborate system of defense. The Maginot Line was a series of fortifications that stretched 200 miles along the eastern French border. It consisted of gun emplacements, barracks, and underground command posts, all connected by railroad tunnels. But as in the past, a new defense spawned a new offense. The heavily mechanized Blitzkrieg outran the French and in swiftly storming through Belgium went around the heavily fortified Maginot Line. Once again, the army that could move faster was the prevailing force. Newly designed airplanes were equipped with much more powerful machine guns and bombs. Vastly improved tanks were faster and armed with more killing power. All of this new technology triggered the stimulus response mechanism of battlefield engineering. Bombers needed airfields. Airfields in turn were bombed and needed to be rebuilt. Bridges were blown up and needed to be replaced or repaired. In response, engineers created prefabricated footbridges, treadway bridges, and dummy bridges as decoys. General Douglas MacArthur, who was himself a top-of-his-class engineer graduate of West Point, described World War II as an engineers' war.
You're watching Battlefield Engineering on Modern Marvels.
The attack on Pearl Harbor in 1941 caused the United States Navy to change the way it built its bases overseas. Until the surprise strike, the Navy had used civilian engineers and workers. But shortly after Pearl Harbor, on Wake Island, 2,300 miles southwest of Hawaii, some civilian workers were captured by the Japanese.
Under the Geneva Convention, these civilians, if they take up arms, are not protected by any of the covenants of war and can be executed as spies. And in a few cases, this actually happened.
Rear Admiral Ben Morrell got the go-ahead to immediately create a naval construction battalion made up of engineers trained to fight. The name Seabees was coined from Seabee, the initials for construction battalions. Their mascot was a fighting bee carrying a machine gun, a wrench, and a hammer.
Mostly our troop, our gang, were from construction companies that the Navy went through and literally just bought out and uniformed up and sent out.
As a result of looking for engineers and tradesmen with some experience, the average Seabee in World War II was in his 30s. Many had wives and children and were exempt from the draft, but volunteered anyway. The much younger Marines had a standing joke: be kind to a Seabee. He might be your father.
These old men in their 30s were the guys who were going to save your bacon and do extraordinary things for you.
Building an airstrip while having to fight off the enemy at the same time often created heroic challenges. Usually a Seabee would put down his tools and fight, but Aurelio Tassona decided to use his bulldozer as a weapon.
The Japanese were in a pillbox. They were holding up an advance on an island, and Aurelio Tassoni drove his bulldozer up and buried the pillbox, pushed dirt over it, and simply buried it along with the occupants, all except for a dog, a Japanese mascot that survived and was adopted by the battalion.
Another example of Seabee heroics involves Captain Wilfred Painter.
Captain Painter would come ashore in a rubber boat, face blacked out, all the rest, Tommy gun, very dramatic, lay out the bases, the U.S. bases on the island while the Japanese are still there. After he did that, he would leave. Then the Marines would come and take the island, and the Seabees would immediately go ashore and build the bases.
But the most famous example of battlefield engineer heroics must be D-Day, the invasion of Normandy. Long before the actual invasion of Normandy, Allied forces were involved in a massive buildup of men and materiel. The Germans had fortified the French coast with artillery, cement bunkers, barbed wire, and over 1 million mines. The mines posed a serious challenge to the troops who would have to get through them.
As the commander, I felt very strongly that it was necessary to train people to work in a dangerous situation.
Creating that pressure-filled situation in advance involved using live booby-trap mines. One soldier lost his life in the training. Other soldiers cracked under the strain of finding and defusing mines that could blow up at any moment.
When we got through, when it came to a question in France of removing the mines, we knew who were capable of doing it, and those people were used, and people who we found were not able to were given other missions.
In addition to heavily fortifying the coastline, the Germans held all the ports. An invasion without a harbor to land supplies would have been not only foolhardy, but suicidal. The audacious solution of the Allied battlefield engineers was both highly complex and daringly simple. It was called Operation Mulberry, and it involved building a harbor in pieces and floating it across the English Channel. Those pieces would be moved using a versatile system of construction that used 5-foot by 7-foot metal boxes.
What these was the tried and true pontoon. In this case, put together, 7 long, 3 together, tied here with an outboard engine, and now it becomes a ferry. A flat bed that can carry troops, men, materiel, heavy equipment ashore. You take the same configuration apart with the engine off and lash it together in a long form, and you have a causeway or a pier.
On June 6, 1944, the largest amphibious force ever assembled landed on the beach at Normandy. 4,000 to 5,000 ships, 11,000 planes, and on the first day, 155,000 troops came ashore. Immediately before this massive assault, the combat engineers specially trained to clear mines snuck ashore in the dark to clear the way for these troops. Throughout the attack, the engineers were in the most vulnerable positions.
One of the units lost 67% in wounded or killed. It's pretty hard to do it. Sometimes it would have been easier to pick up a rifle or a machine gun and fire back than to do your job of clearing the way.
Even as troops were still coming ashore, engineers began the construction of the Mulberry Harbor.
The Mulberry system was a system of prefabricated dock facilities that were made of cast concrete, filled with air and floated across the channel, and they were sunk right on the Normandy coast to build our own prefabricated docks.
The first phase involved dynamiting a number of old ships and then sinking a long line of cement caissons. Together, the ships and the caissons would form offshore breakwaters. Next, a floating roadway was built stretching from the shore out to the protected area behind the breakwater. Once a wharf was constructed at the end of that road, it allowed the unloading of tanks, trucks, men, and supplies from larger ships. In less than 2 weeks, the harbor was fully functional. By the end of the month, approximately 1 million men came ashore. In addition to building the artificial harbors at Normandy, the engineers operated the beach camps which housed the troops. They also laid fuel and water lines and ferried back and forth across the channel with more men and supplies. Without the engineers accomplishing all of these tasks successfully, there could have been no Normandy invasion, no D-Day. Once Allied troops were on the European mainland, they faced the difficult task of getting fast-moving tanks across rivers and streams. British engineers developed the Bailey Bridge, a portable structure with no single piece that weighed more than 600 pounds. It was used when there wasn't enough time to build a traditional bridge.
In the infantry, you have the term "hooah," which means, well, let's get going, let's get the job done. In the engineers, we have the term lay, hold, heave, which represents picking up Bailey Bridge panels for construction projects. Lay, hold, heave the bridge panel. And you have soldiers working in unison to build a 10-ton bridge. It's choreographed like a ballet. Everyone has to work together and lift and heave together. It talks about the physical work of the engineers.
The ability to work together to come up with practical solutions in the field is the common link between the battlefield engineers of the past 2,500 years. But as the weapons of war became deadlier and more powerful, the challenge facing the engineers became increasingly more difficult.
You're watching Battlefield Engineering on Modern Marvels.
In 1950, when the Korean War broke out, battlefield engineers were faced with a demolition job. Breaking through fortifications, breaching minefields, and blowing up bases. They were also charged with building vital airfields, bridges, and roads. In addition, they cleared the jungle for mobile Army surgical hospitals, better known as MASH units.
Korea changed dramatically the history of fatalities because before Korea, 90% of all the wounded that were hit in the head or the belly died. And once the MASH were set up, 90% lived because they could get back to the MASH hospitals.
One of the biggest challenges facing the engineers was the lack of raw materials to get the job done.
Cement was not available. Steel was not available. timber was not available. You must remember that everything south, roughly everything south of the 38th parallel, was agriculturally inclined, rice paddies. So it was very innovative engineering. You couldn't do things precisely.
An example of that innovative engineering involved figuring out how to get heavy machinery to operate in sub-zero temperatures. One company kept their bulldozers warm in warming huts and then borrowed another idea from the ski slopes.
The problem was, once the bulldozer got warm, the blades got hot and the frozen earth would stick to the bulldozer blade. So what we did was to radio over to Tokyo and had several thousand pounds of ski wax dropped into our perimeter there, and we used ski wax on the blades, and this enabled the blades to work without the earth freezing onto the blades.
In Korea, because the front line was constantly shifting, one day's advance was often the next day's retreat.
Ironically, sometimes engineers have to destroy what they just built. One engineer battalion in Korea built a 1,000-foot timber bridge for tank and logistical resupply, and a week later had to pour diesel and gasoline on it and burn it. The bridge was ultimately referred to as the Broken Heart Bridge, and the battalion was referred to later as the Broken Heart Battalion.
Despite valiant individual efforts and innovative engineering, broken hearts were the order of the day for many of the soldiers in the Korean conflict. And that would also prove to be true of the United States' next big war. The engineering challenges posed by Vietnam was that, unlike other big wars of the 20th century, there was no front line. This was compounded by the fact that much of the war was being fought in a dense jungle. Since this was the first air mobility war, a primary responsibility of the battlefield engineer was to build and maintain airstrips and helicopter landing bases.
Sometimes the engineers, to get into difficult areas, jungle areas, built-up areas, they had to helicopter in. There they would come down the rope ladders with their hand tools, clear an area for a bigger helicopter to come in, which would be carrying a bulldozer. That type of a base could be built by a company of engineers in about one day.
The almost non-existent infrastructure in Vietnam meant that engineers were basically starting from scratch, having to build roads, drainage and bridges, and having to do it with almost none of the raw materials required. What they did have was plenty of mud.
Among our earliest taskings was the job of getting the Marines up out of the mud so that they could have decent living accommodations when they were not out in the field searching for the Viet Cong and the North Vietnamese. The way we got them out of the mud was to build what's known as a Southeast Asia hut for everyone who was there. We could put in 15, 20, 25 of these an hour once we got the prefab technique down.
The use of pontoon bridges wasn't really practical because the rivers were being used for day-to-day navigation. Instead, conventional cement and steel and timber bridges had to be constructed. To counter the overall lack of dockage space, engineers came up with the Dulong Pier.
Came out of Charleston, South Carolina. It was a barge that was about 300 feet long by 90 feet wide, built in Charleston, towed across the water to Vietnam, and then set in place. A team of 15 engineers could put it into position in about 45 days.
To build a timber pier this size would take 6 months. Another innovation was the instant airstrip, made possible by the use of T-17 nylon membrane. Lighter and easier to transport than metal runway sections, it was glued together over a graded and compacted airstrip. The synthetic material created a surface so strong it could be used by huge aircraft. The introduction of the Rome plow, a rugged bulldozer blade made in Rome, Georgia, was a tremendous asset and aided in the difficult task of clearing a jungle filled with mines. Although the Rome plow could detonate some types of mines without being destroyed itself, most mines still had to be cleared by engineers on foot or in vehicles equipped with mine detectors.
It was actually really scary to a certain extent. You didn't know what was going to happen. The mine detectors were good, and they were bad in the sense that when you're going down a dirt road in a combat zone, there's so much shrapnel, there's just all kinds of metal in the road, so you really had to develop a sense of signal detection to determine whether it was a mine or something, and you never knew for sure what you were going to find.
In addition to the mines, American engineers had to concern themselves with the tunnels built by the Viet Cong, engineering marvels in themselves. In Cu Chi province near Saigon, it was estimated that there were 200 miles of tunnels. Although U.S. forces tried several techniques to eliminate them, none was completely successful.
The Viet Cong tunnel system in some areas was quite extensive. In some areas it was even 2 to 3 layers deep. They could put hospital units down there. They could put maintenance and repair units down into the tunnels. And they were quite extensive and quite effective.
Whether the United States troops would get the cooperation of the local people was often a question mark. But engineers had something extra going for them.
The Seabees mission, in addition to supporting the combat troops, was also to assist the local Vietnamese populace. And so the roads that we built not only supported the U.S. forces, they also were frequently of use to the Vietnamese or the North Vietnamese forces, and they supported the local economy. Therefore, we were able to go places and send single trucks that were marked very clearly with Seabees on them in areas that no one else would dare go.
In a war in which few good things are said about the outcome, the construction projects of the American battlefield engineers may be the most positive, lasting legacy of the conflict. The lessons learned in the jungles of Southeast Asia would some 20 years later be applied in a vastly different arena, the deserts of the Middle East.
You're watching Battlefield Engineering on Modern Marvels.
When U.S. troops started the buildup in Saudi Arabia, the challenge posed by a desert environment was poles apart from the muddy jungles of Vietnam.
You have massed formations of armored vehicles attacking fixed fortifications, something out of World War II, almost. Vietnam was a low-intensity war. It was a brush fire war. You had armored vehicles there, but not in mass, going up against fixed enemy positions such as we found in the desert.
The desert, as any soldier who has ever fought in it will tell you, is an enemy in itself.
The sand was everywhere. It was kind of like dust storm days. The tents would be full of sand. Your gear was, the equipment was, weapons had to be cleaned frequently if they would operate. The challenges were extreme.
One of the extreme challenges was landmines. This time, a new technique was employed to deal with the old problem. Engineers used a MICLIC, or mine-clearing line charge, a device that fires a hose filled with plastic explosives. After being launched across a minefield, it was detonated, creating a safe passageway through the mines. After months of constructing millions of square feet of aircraft aprons, camps for tens of thousands of Marines, and hundreds of acres of ammunition and supply points, the engineers prepared to support the ground assault into Kuwait. The most formidable task facing the battlefield engineers was the road network required by General Schwarzkopf's end-run attack. It spanned more than 30 miles of desert and required more than 200 miles of roads. Some were barely drivable until they were hurriedly improved just before the attack.
Bottom line is, this road was, you know, at the beginning, maybe you could go 5 miles an hour. Towards the end, you could drive 50, 55 miles an hour on it.
Frankly, when you look at Desert Storm and try to apply the lessons to the next war, you got to be careful, because we're probably never going to find that infrastructure again, and we're probably never going to find an enemy again who says, I will sit here and wait for you to build up this amazing combat power.
The future of battlefield engineering is as difficult to predict as tomorrow's headlines. But the U.S. Army is now preparing for adversaries who might use low-tech devices to combat high-tech weaponry. To counter this, engineers are developing ways to deal with what they call an asymmetric threat.
A mine or an obstacle is a classic asymmetric threat because the enemy can put it in and then leave. He doesn't have any of his forces at risk, but when we get there, it slows us down, it takes us out of our plan, or it kills us.
To counter this threat, the Army is developing new strategies.
What we're trying to do in the future is to replace men with machinery, with mechanization, put fewer soldiers at risk, and do it faster.
One of the weapon systems of the future which exists today is the M1 Breacher, better known as the Grizzly. It is equipped with mine-detecting radar and designed to break through almost any kind of obstacle. Its most visible feature is a mine-clearing blade that can maintain a steady depth of 15 inches as it plows a 14-foot wide path through minefields.
The Grizzly is our replacement for what we today call the orchestrated ballet of farm implements. And what we're trying to do with the Grizzly is get a tank platform that can keep up with our forces and is survivable, that can go in and replace all those soldiers and pieces of equipment. It makes the job for the commander on the battlefield much easier, and it maintains the tempo, because all he has to do is decide where he wants to do the breach, slow down the enemy's rate of fire, and tell the Grizzly operators, create a lane for me.
The Wolverine consists of a computer-controlled aluminum bridge on an Abrams tank chassis. The 75-foot bridge only takes 4 minutes to deploy, and it can be picked up in less than 10 minutes for use elsewhere.
An M1 tank weighs about 70 tons. There are a lot of bridges we can't put it over, and there are a lot of bridges that our enemies are going to blow up in front of us to keep us from crossing. So we need a way to rapidly bridge small gaps. And the Wolverine gives that to us in a platform that can keep up with a tank.
To cross much larger gaps of up to 120 feet, engineers will use this quickly deployed bridge.
With the heavy dry support bridge, we're going to take the mission that would take a company of 100 or more soldiers all day to build, and we're going to build that same bridge in about an hour and a half with 14 people.
It is now the task of battlefield engineers to do more with less. But while their numbers may diminish, their importance seems to grow.
Without the engineer, quite often the bombers would not fly. The tanks wouldn't cross the river, and the infantry wouldn't advance.
So the mission 2,000 years ago was the same as it was in Desert Storm, where we built roads through the desert, we built bunkers and barracks facilities, and we brought water to our troops. So the mission hasn't changed. The only thing that's changed has been the technology.
In the final analysis, despite the downsizing of the military, the fact remains that someone will be needed to operate the machines being used to replace the troops. If history is any guide, those operators will be battlefield engineers.